Now it's time to cover Chapter 2. Chapter 2 is all about descriptive statistics. In this chapter, we will learn to organize data, describe data, present descriptive statistics, and this chapter gives us the foundation for organizing and presenting data that was gathered from a study. So this is, if we already have data gathered, what are we going to do to organize it in a manner that allows us to describe it using means, medians, modes, something called a 5-number summary. We can talk about standard deviations and other descriptive statistics that we can calculate from data that we've collected. We're going to be focusing primarily in this chapter on quantitative data because that's the type of data that you oftentimes will run across. You absolutely can do these sorts of things with qualitative data as well. Obviously, you're not calculating statistics there, but qualitative data, you can organize it and describe it as well. But we're going to focus on the quantitative data as we go through this chapter. As we start out, we want to talk about frequency distribution tables. So frequency distribution tables is kind of our first thing that we do to organize our data. And so say we have this data here where we have 18 students that were asked how many hours they worked per day. And their responses in hours are as follows. And so we have this nice little list here of 18 numbers, and that really doesn't do much for us for trying to think about and summarize this data. Just by glancing at this, we don't have much of an idea of what's going on with our data. But we could go through there and say, hey, there's multiple times that we see a 5, lots of times that we see a 3, and what other values do we see? Well, all the values that we see is 2, 3, 4, 5, 6, and 7. And we could go through and create a table here where we list all of the data values that we see, and then we list the frequency that each one occurs. So we could go through and see that the data value 2 occurs 3 times, the data value 3 occurs 5 times, data value 4 occurs 3 times, the frequency of the data value 5 is 5, the frequency for 6 is 1, and the frequency for 7 is 1. Now, looking at this table, we kind of get a little bit more of an idea of what's going on. Not very many students work more than 5 hours. And in fact, we could say that, most students work between 3 and 5 hours. Now, this sort of summarization into a group frequency distribution table like this, or frequency distribution table like this, works well if we have a small amount of different data values that we could look at. So like here we have 2, 3, 4, 5, 6, and 7. So we only have 5 different data values that we're looking at. But what if there was a data set that had 100 data values in it and there was 20 different values that things assumed? So each of the values would occur a few times, but there's 20 separate data values that our data could be. It wouldn't be very organized or do us much to look at it if we organize it like this. So instead, we use something called a grouped frequency distribution table. So a group frequency distribution table will group data together. It groups data together based on values that are numerically close to each other. So this is useful when there's a large number of data values that vary over a large range. To calculate some things for this, we want to make sure that we know how to calculate the range. So the range is your maximum data value minus your minimum data value. We're going to first find the range when we're trying to construct a group frequency distribution table. Then after that, we were going to start thinking about how to arrange things. So instead of having each row be a different data value, it's going to be a class of data values. So data will be arranged in classes that's identified by limits. So class limits, there's going to be lower limit and an upper limit, and this is the smallest and the largest data values that can go into the class. These have the same accuracy as the data, and what the same accuracy as the data means is that if your data is accurate to 1 decimal place, then your class limits will be listed to 1 decimal place. If your data is all whole numbers, then your limits will all be whole numbers. Now, when thinking about your class limits and constructing this group frequency distribution table, we want to think about, well, how many numbers are we going to put into one class together? And that really depends on the number of groups that you want to have for your grouped frequency distribution table. So your class width, or basically the amount of the range of data values that can fit into each individual class, is called the class width. So it's the difference between your consecutive lower or consecutive upper class limits. And you can also calculate it by taking the range divided by the number of groups that you desire and then rounding up. So if you are working on constructing a grouped frequency distribution table, then you would probably use this second one here. But if you have a group frequency distribution table in front of you, then you would be more apt to think about the class width by using that first bullet. All right, so a little bit more about group frequency distribution tables. Once all of your data is arranged in your group frequency distribution table, we can talk about boundaries and midpoints of classes. And so the boundaries are kind of your halfway point in between one class and the next. So to find this, you'd average the upper class limit with the lower class limit of the next class. And your class boundaries will then end up with one more degrees of accuracy than your data. So if your data is accurate to a whole number, then your class boundary will be accurate to one decimal place. Your class midpoint is going to be that average of your values in your class. So you're going to average your lower and your upper class limits. And when I say averaging your upper and lower class limits, I'm saying add them together and divide by 2. So there's a bunch of information there on the last 2 slides about group frequency distribution tables, but we still need to work a little bit more on calculating our group frequency distribution tables. So constructing a group frequency distribution table, the first thing you want to do is to go ahead and find your class width. The class width is your range divided by your number of classes. And remember that we're always going to round up. Pay attention to if you're given any sort of special directions, such as the class width should be a multiple of 5. So sometimes you might have to do a little bit of special rounding there. Then you'll select your first lower limit, and your first lower limit should be equal to or just a little smaller than your minimum data value. Again, pay attention to if you're given any special directions, such as a lower class limit should be multiples of the width. So pay attention to those sorts of things as well. But so when finding class width, you're going to take your range divided by number of classes and then round up. And then you'll select your lower limit so that it's equal to or just a little smaller than your data value, or your minimum data value. And then you're going to calculate your remaining class limits using your class width as a guide. And then that gives you all of your classes. And then to fill in the frequencies, you're just counting the number of data values that fall into each class. So with that being said, I think we're ready to go ahead and try to construct a grouped frequency distribution table together. And this example here that we're going to see has a few special instructions with it. Just like I mentioned on the previous slide, we always want to pay attention to if it has special instructions. So it says, create a grouped frequency distribution table from the following data over a number of 5Ks run by individuals. Choose a nice class width, so either a multiple of 5 or a multiple of 10. Each class lower limit should be multiples of the class width, and it says that there should be 10 classes. So the first thing here that we're going to do is we're going to go ahead and find the range. So the range is your maximum data value minus your minimum data value. So we're going to do 246 minus 2. That gives us 244. And then to find our width, we're going to divide by the number of classes that we desire. We desire to have 10 classes. So we'll do 244 divided by 10. That gives us 24.4. And we'll round that on up to 25. So now we have our class width. And we're going to go ahead and label our limits and list our frequencies. So as we're going through here, the first thing that we want to do is make sure that we find the correct minimum data value. So our correct first lower limit. And we're looking at our minimum data value when we're doing that. Our minimum data value is 2. And we want to make sure that our first lower limit is equal to 2 or just smaller than 2. And looking at our special instructions here, it says each lower limit should be a multiple of the class width. So we need something that is a multiple of our class width, which is 25, but is smaller than 2. 0 is a multiple of anything. So in this case, we could use 0. Now, I am going to do a little bit of writing by hand on here, and then I'll replace it with typed font and afterwards. But if we go through here, we would start with saying, okay, 0. And I always do all my lower limits first. So 0, and the next one would be adding 25. We have 25, and then 50, 75, 100, 125, 150, 175, 200, 225. And then for the upper limits of a class should be 1 less than the lower limit of the next class. So we should have 24 for our first upper limit. And then again, we could just go along and add 25 each time if we wanted to, instead of always subtracting 1. So you can either always subtract 1 or just continually add your class width when you're creating these. And here, having a nice class width being a multiple of 5 kind of helps here, because we all know our multiples of 25 fairly well. It's fairly easy to count by 25 compared to like counting by 23 or something like that. So we'd have all of our classes listed. And then we would want to go through and list the frequency for each class. And listing the frequency for each class, there's a few different ways you can go about it. You can go through your list and go like number by number and say like, oh, hey, where is 133? 133 would be in this class, and then you'd mark it off your list. Some people also prefer to go through it by saying, oh, I'm going to look for all the values that are in the first class, look for all the values that are in the second class, and mark them off as they go. I'm of the first group where you say, okay, 133, that's in this category. I lost it. I don't know what happened. I'm just going to keep going. Okay, we have it back. My handwriting's gone though, which is fine. Now you can see the typed stuff. I'm not re-recording my lectures. That's just a one shot and we're done. So you'll just enjoy my mistakes as we go this semester. You'll laugh at my technical difficulties. Okay, so we're working on frequencies. I'm just going to abbreviate to freak. Okay, and then I'm of the group that says, okay, 133, what category does that fall into? It falls into that class, and then marking it off. So I'm going to go across and I'm going to tally, and then after I've tallied, I will go through and add them up and actually write the numbers in there. And when you do get numbers that are on those endpoints of your class limits, that's okay. They fall into the class that you have there. So make sure that you're putting them in the correct class each time. close the way there. Now it looks like I have all my tallies done. So then I'd go through, let's say that's 1, 5, 2, 6, 6, 5, 1, 1, 0, 1. And to see it nicely typed out, there you have it. One thing that you can do to make sure that you didn't accidentally forget to count one of them is you can go through and you can add your frequencies together. If you add your frequencies all up, you should get the total number of data values that you started with. So this is your group frequency distribution table. You will be creating one of these on your homework, and it will have these special instructions of, having a nice class width and your lower limit being a multiple of the class width. And this is just for consistency with assignments and for me to be able to have the computer grade your work a little more easily. Now, looking at this group frequency distribution table, we can definitely see a little bit more about our data than we could with it being listed out. And there's only 28 data values here. And so it's interesting how much easier grouping it into just 10 classes can make it to see how our data is distributed. We see that most of our data values are in that 4th and that 5th class there. A little bit into that 6th class as well. Now, it's kind of nicer looking at this group frequency distribution table, but everybody wants to have a nice picture to look at, right? So what kind of pictures can we draw to make this easier to read? If I was going to present this information in a paper or do a talk over it, instead of listing my data like this, I would probably want to have a nice looking graph. Well, the go-to graph for if you have a grouped frequency distribution table is a histogram. So histograms use the data from grouped frequency distribution tables. It uses bars to represent group frequencies. It kind of looks like a bar graph, except for the difference between it and a bar graph is with a histogram, the bars always touch. With a bar graph, the bars don't touch. Your class boundaries will be used along the x-axis, and the frequencies will be found along the y-axis. And whenever you're drawing a graph, do always make sure that you're labeling both the axes and giving the graph a title. Now, you're not going to find yourself creating a histogram on the homework, but at the end of the semester, there is a project that you will do. And in that project, you will most likely want to create a graph of some sort. And one such graph is a histogram. So let's go ahead and do an example where we take that data that we have already and we construct a histogram with this data. So we already have our group frequency distribution table. Now we just need to find our class boundaries. So going through and calculating class boundaries, we're thinking, okay, we're going to average together lower limit with the next upper limit. Now, I'm going to leave kind of a little bit of a blank spot here because that first lower limit is kind of one of the harder ones to find. And then we'll find that first upper boundary and continue on, and then we'll come back and find that first one there. So we're going to leave that blank and we're going to find the next one. So we're going to find this next one by taking 24 plus 25, dividing by 2, and getting 24.5. Basically, we're saying what is exactly in the middle of 24 and 25? And what's 24.5? So we're going to have little intervals going here. And we're going to see that these two values always match along this diagonal. So the next one, 49 plus 50 divided by 2 is 49.5. And I like to think of the boundaries as kind of like a fence that you build between your property and your neighbors. Your property goes right up to that fence. There's property starts right after that fence. So that's kind of how I think of these boundaries. And I know my handwriting's a little bit sloppy, but you're following along great on your paper. So keep up the hard work. Whoops. There we go. Okay, we have all but our very first lower boundary and our final upper boundary. And these we've got to stop and think a little bit in order to come up with them. Now, what you might notice as you're looking at these um, is we could think about, like, if there was a class above or below these classes, what would those limits be to help us create those boundaries? Um, we can also think of it as looking at the difference between consecutive uh, boundaries, and saying, oh, hey, it should always be 25 between my boundaries still, just like it's 25 for my class width. And that can help us calculate it as well. But what we'll notice is this upper boundary is going to be 249.5, and this first one's going to be negative 0.5. If you're thinking about what the class would be that's below this, its upper limit would be -1. So you'd average -1 and 0, and you get -0.5. And you can play the same sort of game with the final class, saying, okay, if there was another class after it, it's lower limit, and you'd say, oh, well, it would be 250, and then you can go through and say, well, then averaging them, you have 249.5. But so we have all of our boundaries constructed. Here you see it nicely typed. And we start creating our graph. So creating a graph, we have to have axes, both an x-axis and a y-axis. And so then we want to make sure that we are labeling them. So we have our y-axis labeled. We want to give it a title or a description over there as well, in addition to just calling it the y-axis. So we're going to call it the frequency, because along the y-axis, we always have frequency when we're dealing with histograms. And then, we're going to go ahead and put values along there. So our frequencies range from 0 all the way up to 6. So, 0 is along the bottom, along that where the x-axis meets the y-axis. And then we'll use 1 tick mark for each value going up. So we have all the way up to 6. Then we label our x-axis. We give it, a description down there of number of 5Ks that were run. And we're putting our boundaries along here. And, keep in mind that your x-axis is a number line. And, seeing as it's a number line, we should have, sequential numbers along there, evenly spaced. So we're starting with that first lower boundary, -0.5, and then we use the next boundary, which is 24.5, and then we use the next boundary, which is 49.5. Just because we have 24.5 listed twice as an upper boundary and a lower boundary does not mean that we list it twice here on our histogram. They're shared. It's that shared fence in between the properties. And so it's only listed once for each of them as we're going across the x-axis. Now, this graph should probably have a title. This is about the 5Ks that were ran by individuals. And now we can start going ahead and drawing in our vertical bars. And our vertical bars, we want to make sure that they are always touching, and that their height corresponds with the frequency for that class. Now we could look at this graph, and we could give a little bit of a description as to what's going on. So by looking at this, we see that by and large, our data values, or the number of 5Ks that have been ran by an individual, is between 74.5 and 149.5. You might also mention that, there's another spot where there's a high point that there was quite a few individuals that had ran between 24.5 and 49.5 5Ks as well. So that kind of like gives you a way of starting to describe your data visually. Whenever you do have a histogram, you do want to make sure that you do kind of include a little bit of an analysis of it. If you're giving a presentation, you're going to talk about what it looks like, what shape it has. If you're doing a paper, you're going to write about that. And as we're thinking about describing these, we want to talk about shapes of distributions that are kind of known and talked about. And so there's 8 shapes that we're going to go over. What we have is the bell-shaped first, and this bell shape is a shape that we're going to talk about quite a bit. So the bell shape is right here, and this bell shape it kind of starts off small, and then it works its way up, and then it works its way back down. So it's a nice symmetrical distribution where there's a peak in the middle, and there's only one peak. And that peak, where it peaks, we tend to call that a mode. So we would say that this is unimodal, meaning there's only one mode. And saying that it's symmetrical lets us know that the mode is there in the middle and it tapers off on both ends. Uniform distributions tend to be fairly flat going across. So a uniform distribution might have a little bit of variation in frequency for each class, but overall it's fairly level. Next, we have the J shape. The J shape all the way to the right is where the mode is, and it's just each class is increasing heading towards there. The reverse J is the opposite. The smallest class is going to have the largest frequency, and then it tapers off. Now, as long as the distribution for the most part looks like one of these shapes, we could say that it's approximately this shape, even if it doesn't fit it perfectly. And there's still 4 more shapes that we're going to look at and talk about a little bit. So the next ones that we're going to talk about is the right skewed and the left skewed. And you might say by looking at them, well, you know, those look kind of like the bell shape. Well, they do look kind of like the bell shape. But you might notice that, hey, the right skewed has a little bit of extra data hanging there on the right. So basically, it's like you're thinking, okay, if I covered up the right side of this distribution, took it off, it's going to look like a bell shape. And so you could say that it's a right skewed distribution. You could say that it kind of looks like a bell, but it's skewed to the right. And then with the left skewed, again, if you take off the left side, then it's looking more like a bell shape, and definitely not like a perfect bell. But this kind of gives you an idea of skewing some of your distributions and what that might look like. Another popular one to talk about is the bimodal. So a bimodal distribution is going to have 2 spots where we have a little bit of a peak. Looking at the distribution that we just graphed a histogram for, we could call that one bimodal because there was 2 different spots where there was a peak. Now, you might say, well, what's the difference between the bimodal and the U-shaped? Both of them have 2 different modes. Well, the difference here is the 2 modes in a U-shape are all the way on the ends. And this gives it a nice U shape as you're looking at it, kind of like the opposite of a nice pretty bell. And so a U-shaped is going to be a bimodal distribution where your 2 different modes are occurring on opposite ends of the spectrum of your data values. There is another type of graph that we could draw based on our frequency distribution table, and that's called a frequency polygon. So frequency polygon, instead of using bars, it's going to use some dots and some lines, and we're going to end up creating a polygon with all of this. So it uses the data from a group frequency distribution table, and it uses dots at the class midpoints to represent the different class frequencies. It uses the midpoints along the x-axis and the frequencies along the y-axis. So our dots are going to be connected by lines, and these lines are anchored to the x-axis before and after the data exists. And then what this does is it creates a polygon between this line and the x-axis. We always want to make sure that we label our axes and give our graph a title. So again, look at the same data set that we've had from before. We have our classes, our frequency, and if we're going to do a frequency polygon, we need class midpoints. Class midpoints are calculated by taking and averaging the lower limit with the upper limit. So the first class midpoint, we'd take 0 plus 24, divide by 2, so we'd get 12. Then the next one, 25 plus 49, and then divide by 2, we get 37, and so on. So we get all of our different class midpoints here. And then again, we're going to go through and we're going to draw our graph. So we have our axes, label, we have a title going on. Make sure that we get all of these details in there. And then we have our x-axis with our midpoints listed along it. Now above each midpoint, we are going to go ahead and put a dot to represent the frequency. So above 12, we're going to be at frequency 1. And then we're at frequency 5, then 2, then 6, and 6, and 5, and 1, and 1, 0, and 1. And then after that, you start drawing in lines. First, we want to draw a line to anchor that first one to the x-axis before our first data value. And then we continue to draw, connecting each of these, going from left to right. And then finally on the end, we are connecting it to the x-axis after the data values. So we've created a funky looking polygon here. And again, it has the same sort of a shape and things that we can notice and characteristics as what we talked about with our histograms. Now, there's other types of data out there that we could talk about that would require different types of graphs. One such graph that's fairly commonly seen is the time series graph. So a time series graph represents data over time. So you'd have time along your x-axis in whatever units your time is in. And, it could be in minutes or hours or days or months or years. And then along the y-axis, we're going to have an amount or a frequency. And we're going to use dots here. So we'll have a dot representing all of our data points. And then we're just going to connect them with lines. On this one, we do not anchor it to the x-axis. Again, always make sure that you label both axes and make sure to give your graph a title. So let's create a time series graph for the following data set about milk prices. And this is data that was pulled from the interwebs from quite a while ago. And I don't even remember what town I was looking at when I pulled it. But so this is data from the internet. And it's an average milk price in a certain town over a month. So in January, the average milk price was $2.30. And we can see that it changed as the year went. So we want to make sure that we give a title to this. We're talking about milk prices here. We have the cost of milk going to be along our y-axis. And when I created this, I decided to go in units of 7. You can choose anything that you want to. We see that I have a little break down here at the bottom. This little squiggle here, that's saying that there's a break in the graph, that we're not showing all the way down to the x-axis. This kind of just allows you to zoom in a little bit on your data. If you're doing that, make sure that you do include that little break there as you draw it. Along the x-axis, we have our different months. So label all your months along there and write month. And then we just start plotting our data going along. And once we have our data plotted, we're drawing lines. And there we have it, a time series graph. So now we kind of know a little bit about just organizing and presenting our data in a way that is nice to look at, and helps people kind of get a feel for what's going on with the data. But we haven't done yet is to start talking about how to summarize our data with just a few numbers, or talking about, where our data is located within the data set, or where it is relative to the mean. Um, and so we want to kind of shift gears into talking about data and the data values, and their relation to each other, and just some nice summary statistics that we can use to talk about them. So we're going to talk about data location. When thinking about data, occasionally it's useful to know where the data value is located within the set. So two useful tools that we have for talking about this would be percentiles and quantiles, or quartiles. So percentiles break the location into 100 groupings. A percentile location identifies the percentage of the data that falls below that data value. Quartiles are special percentiles that break the location down into 4 groupings. So we have our first quartile, or the 25th percentile, the second quartile, which is the 50th percentile, which is also known as the median. And you can see some abbreviations are being listed here as well for you. And then we have our third quartile, which is also the 75th percentile. We're going to talk about quartiles first just a little bit, because they're a little bit nicer to work with. So when finding quartiles, we're going to order our data from smallest to largest. And then we're going to start by finding the median. And finding the median is kind of the easier thing to do, because it's the value that's exactly in the middle. So if you have an odd number of data values, then you're going to have a number that's exactly in the middle. And you're just going to find the number exactly in the middle, and there's your median. Ta-da! If there's not a number exactly in the middle, because you have an even number of data values, then you're going to take those two data values that share the middle, you're going to add them together and divide by 2. So now we have our median. And essentially we've split our data into the lower half and the upper half. If you have an odd number of data values, that median is one of your data values, and it's not included in the lower half or the upper half. If you had an even number of data values, those two numbers that shared the middle, one of them is in the lower half and one of them is in the upper half. And we'll kind of see that as we look at a few examples in just a bit. Now to find the first and the third quartiles, we're just going to repeat this process using just the lower half of the data, find the median there, that gives us our first quartile, then use the upper half of the data, find the median there, and that's our third quartile. Sometimes it's useful to talk about the interquartile range. This is the distance between our first quartile and our third quartile. So the interquartile range is abbreviated as IQR, and that is our third quartile minus the first quartile. This is helpful in finding outliers in case you were interested in identifying if something was an outlier. So if a number is smaller than our first quartile minus 1.5 times the interquartile range, then it's an outlier. If a number is greater than our third quartile plus 1.5 times the interquartile range, then we can consider it an outlier. So let's go ahead and construct a 5-number summary from this data. And a 5-number summary is our minimum, our first quartile, median, third quartile, and maximum. Now, our minimum data value is probably going to be fairly nice to find, especially if we have our data arranged from smallest to largest already, which I've nicely arranged it for us here. So our minimum data value, easy to spot, it's 2. It's also pretty nice to spot our maximum data value. Our maximum data value over there on the right is 32. Now we can look through here and try to determine what our median is. So looking through here, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 data values. We have 17 data values, which means there is a number that is exactly in the middle. So let's go through again, kind of thinking which number is exactly in the middle. And I tend to mark them off or make some sort of marking working my way into the middle. And this 14 is left here in the middle. And we can verify that the count of numbers below it and the count of numbers above it is equal. So 1, 2, 3, 4, 5, 6, 7, 8 below, 1, 2, 3, 4, 5, 6, 7, 8 above. So we would say that 14 is the median. Now, we're going to repeat this process looking at only the lower half in order to find the first quartile. So looking at just the values that I have boxed in blue, we're going to find the median again. And this is going to give us our first quartile. So going through it again, we can go through and count and make sure we have an odd or even number. If you remember, we counted, we had 8 values. So that means there's going to be 2 values that are going to share the middle. So we have, marking them off again, 8 and 9 share the middle. That means our median for our lower half, or our first quartile, is exactly between 8 and 9. So we'd add those two together and divide by 2, and we'd get 8.5. Then we'd come over to the other side. We'd work with the upper half of the data set. And working with the upper half of the data set, we do the same thing over again, marking them off till we come up with the 2 that share the middle. And 18 and 20 share the middle. That means the third quartile is exactly between them. Averaging 18 and 20, we get 19. So we've come up with a nice 5-number summary here. So we have our minimum, first quartile, median, third quartile, and our maximum. Now, this 5-number summary is useful graphically occasionally by using something called a box plot or a box and whiskers plot. So graphical representations of the quartiles along with the minimum and maximum data value, it's called a box plot. And so here's an example of a box plot. So basically you're taking your minimum value and you're drawing a vertical line for your minimum value and then a vertical line for your maximum value. And then in the middle, we're going to also do vertical lines for our quartiles and our median. But those inside 3, we're going to make a box out of. And then we use just one horizontal line going out to our minimum and our maximum value. So it makes kind of a box with some whiskers coming off of it. So hence the name box and whiskers plot. Now with our box plots, we can talk about the shape of data. So for a nice bell shape, most of your data is fairly close together. So if we wanted to think about a nice bell shape, and I'm not going to draw the x-axis below, I'm just going to draw a box plot. So a bell shape, maybe we have a nice box. That median is going to kind of be right there in the middle of it. And then we're going to have decently long whiskers. In contrast, more of like a uniform distribution would have the distance between each of these values would be about the same. So that would look more like a uniform. So we have bell, we have uniform, and then we could think about our left skewed and our right skewed fairly easily as well, based on our tails. Which side do we have extra data on? So if your tail is extra long on the left, it would be left skewed. If your tail's extra long on the right, it would be right skewed. So we kind of talked a little bit about our quartiles and graphically representing them. Now we want to get into talking about the percentiles, which is where we're breaking our data up into like 100 groupings and saying, okay, where is our data located? And throughout your life, you're going to see percentiles in quite a few places. So like one place that you'll often see percentiles is if you ever have kids, or if you remember when you were a kid, going to the doctor and being told something about, being in a certain percentile for height or for weight, or or for head circumference or whatever measurements they're taking on you. And as a mom of young children, I'm constantly going to the doctor and I'm hearing, oh, they're in this percentile or that percentile. And my two daughters, they were born, and for most of their first year, they were like the 10th percentile or smaller. One of them was in the second percentile for a while. And then my son came along when he was born, and he was in the 99th percentile when he was born. Well, what does that mean? Okay, well, I'll play the game. What does that mean? Well, what it means is 99% of babies that were the same gender as him were smaller, meaning only 1% of babies were bigger than him. Then for my girls, the one that was in the second percentile for a while, for that gender, for that age, only 2% were smaller than them, meaning 98% were larger than them. So I had small girls and a big boy. But so that's what percentiles talk about. They kind of tell you the position within the data, showing you what percent is below and then helping you think about then what percent is above. You'll also see percentiles when you are in grade school, and you get a report from the standardized test showing you what percentile you scored in, and like your parents were like, oh look, you scored in the 80th percentile, you're so smart, and you'd be like, got an 80%. I mean, that's not super great. Well, actually, an 80th percentile is really pretty good. That means you're smarter than 80% of kids your age, and so we want to make sure that we're able to talk about this, because being in the 50th percentile means you're average. It doesn't mean that you failed the test. So we want to make sure that we know what percentiles are and also how to find percentiles. So finding percentiles. One of the formulas that we have for finding percentiles is this formula here. So say like we wanted to know what data value would put you in the 50th percentile. Well, then we'd say that K is 50, and we'd let N equal the total number of data values, and we'd find this value I, where I is the ranking of the position of the data value. And then if I is an integer, then the kth percentile is the data value in the ith position. If I is not an integer, then you're going to round up and round down to the nearest integers and average those two data values in these two positions from our ordered data set. And we're going to see an example in just a minute of this. But basically, we're using this formula at the top here to find the value for I. And I is telling us our index. It's the ranking or the position of the data value that we're wanting to talk about. Most of the time, I is not going to be an integer. So say that we got that I equaled 3.4. We're just going to say I equaled 3.4. Well, if I equaled 3.4, then that means we're going to look at the third and the fourth positions. I don't know why I went up and wrote third and down and wrote fourth, because I know that third is rounding down and fourth is rounding up, okay? I'm thinking like ordering from top to bottom, third and then fourth. My brain doesn't always make super sense. Okay, so we have our third and fourth positions that we're going to look at. Alrighty, so then whatever data value is in the third position, maybe this data value is 56. Fourth position, maybe this data value is 58. Then we'd average and we would find the data value is 57. I'll give you another example here. I'll write it towards the top. So what if we found that I was 5.9? If I was 5.9, that means we're looking in the fifth position and the sixth position. So maybe the fifth value was 7. The sixth value was maybe 12. So you take 7 and 12, add them together, then divide by 2, and you get the data value 9.5 is in the percentile that you're looking at. Now, because I just gave you I and you didn't have K and N, we can't say what percentile it's in. This kind of gets us an idea of what to do once we have I. Now, sometimes instead of saying I want a data value that's in a certain percentile, we start with a data value and we say I want to know what percentile this data value is in. All right, so the expression for finding the percentile of a data value is x plus 0.5y divided by n and then multiply by 100, where x is the number of values counting from the bottom of your data list up to but not including the data value for which you're trying to find the percentile of. So like you're saying, how many data values are a smaller value than the data value I'm looking at? That's what x is how many are smaller. And then y is going to be the number of data values equal to the data value for which you want to find the percentile. So you're thinking, what's the frequency of the data value that I'm looking at that I'm trying to find the percentile of? And then n, as before, is the total number of data values. And what we're going to find as we go throughout this entire semester, that n is going to be our total or our sample size or our sample. It's our total frequency. So n is always going to be talking about how many were in our data set. So let's do some examples of using both of these formulas. And we're going to use the same data set that we just looked at a little bit ago, because I just was not creative when I was picking out data sets. Why create a new one when you've already got one? So let's find the value that represents the 35th percentile. So to find the value that represents the 35th percentile, we need to find I. So to find I, we're using that formula, k over 100 times n plus 1, where k is 35, and we have 17 data values, so n is 17. So I equals k over 100 times n plus 1. So that's 35 over 100 times 17 plus 1. So 35 divided by 100 times 18 gives us 6.3. So what that tells us is we need to look at the 6th position and we need to look at the 7th position. In the 6th position, so counting along, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just going to label all of them. That's going to help us for the second part anyway. We've labeled all of them. The 6th position is 10, and the 7th position is 10. And then we're going to average the values in each of them. And that wasn't too exciting because 10 plus 10 divided by 2 gives us 10. So the value that represents the 35th percentile is 10. How about this? What percentile does 23 represent? And I'll go ahead and circle 23 because we are looking for the percentile that it is in. So to find this, what we're going to be doing is we're going to be using that formula x, where x represents the number of data values that are smaller than the data value that we're looking at. Here, there's how many data values smaller than that? There's 14. And then we're going to say plus 0.5 times y. Y is the frequency of our data value, so y is going to be 1. And then we divide by n, which is the total number of data values that we have, which it would be 17 here. And then we're going to take it times 100. So our percentile is equal to, after doing all the math, make sure that you do things in your numerator and then you divide, following order of operations here. And then at the end, we're multiplying by 100. We get 85.29. We would round this in the nearest whole number. So we'd say 23 represents the 85th percentile. All right, we're most of the way through the chapter. We still need to talk about means or averages, and then we'll talk about standard deviations and a little bit more that has to do with the two of those. So thinking about a mean or an average. So far we've talked about these a little bit and we kind of have sort of an idea going on of what we're going to do when we do this. We're thinking we're going to add all of our values up and then we're going to divide by the number of data values that we have. And that's exactly what our formula is. We can also find the mean or your average if we're looking at a grouped frequency distribution table. It's not going to be exact, but it'll be a nice approximation of it. So what we have here is mu, the mean, and you'll see Greek symbols throughout the semester, but this symbol here is mu. It's a Greek letter, and it stands for the mean, but mu is equal to the summation of f times m, where f is the interval frequencies and m is your interval midpoints. So it'd be your frequency times its midpoint, And you'll do that for all of your classes, and you're adding them all up. And then your denominator is the sum of your frequencies. Remember, the sum of the frequencies is the number of data values that you have. So really our denominators are the same between these two. But this just gives you an approximation here. So this gives you an approximation. I'm not sure if I spelled that right. And if I didn't, don't correct me, please. I do math, not English, okay? I try to spell correctly, and then spell check corrects me, all right? So we have an approximation here using this formula. Now, you're also going to see sometimes another symbol, X bar, and but this symbol here, this is pronounced X bar, and this is our sample statistic. So mu is talking about the population, so this would be a parameter, and then X bar is talking about a sample, so this would be a nice example of a statistic. And the formula for finding mu and X bar is the same, but I want to make sure that you do understand that your sample mean is not always equal to or exactly equal to your population mean. It's a nice approximation for it, but they're not equal, but their formulas for calculating them are equal, which is why I've written that they're equal on this slide. So let's go ahead and do an example. We're going to do a fairly small example here. We're going to find the mean given this data set. So finding the mean, adding all of them up, then we're going to divide by the number that we have. So adding all of them up, divide by 17. We get 242 divided by 17, or 14.23529,412. Well, where do we round to? A rule of thumb tells you to always round your means to one more decimal place or one more degree of accuracy than your raw data. So we'd round to about 14.2. Now, if we were going to use this value in calculations later on, we would keep more decimal places. You should always keep at least 2 more decimal places than what you would want to round your final answer to if you are using it in future calculations. Okay, what if I said we have this data set from before, our group frequency distribution table. We found our class midpoints already, and I say, let's go ahead and find the mean. Well, we could use that formula that I gave you a couple slides ago, saying take your frequency times your midpoint, and then we're going to add those all together. That's going to be our numerator. And then we'll divide by the sum of the frequencies. So essentially what this is saying is we're going to make this assumption that each value in each class is exactly equal to its midpoint. Now, that's sometimes true, sometimes not true. And the larger the data set that you have, the better that this works out. Our data set isn't too big, but we'll see that it still works fairly well. So we take our frequency times our midpoint for each of our classes. And then we add our frequencies for the denominator. We add the frequency times midpoint column for the numerator. We go ahead and divide, we get 99.5. Now, since we do have access to the data set, we could go through and add all of our data values together and then divide by 28, the number of data values that we have, and we get 100.25, or rounding 100.3. So we actually see that our 2 different ways of calculating the mean here are fairly close. Whenever you do have your data set, you should go ahead and actually calculate it using this formula over here. If you don't have your data set, if for some reason you only have your group frequency distribution table, that's when this is acceptable. All right, so when we find the mean, we know where our data is kind of centered at, what it averages out to be. But what we don't know is how spread out or compact together our data is. So we need a tool to talk about that. And that tool that we have is our standard deviation. And we also think variance when we're thinking this. So our standard deviation is a nice little messy formula here. And there's two different formulas, one for if we are looking at a sample and one for if we're looking at the entire population. So we're using S if we're talking about a statistic. And we use sigma if we're talking about a population parameter. I'll just write parameter. And this is called sigma. And you'll notice the difference between these is what we have in our denominator, and also if we have the sample mean or the population mean available to us. Now, the standard deviation is useful for calculations when discussing the theory of statistics. One needs to use the variance instead. So if we're doing calculations, we need standard deviation. If we need to talk about the theory of statistics, then we would talk about variance. Standard deviation and variance are very closely related. In fact, standard deviation is the square root of the variance. So you could say that variance is S squared or sigma squared, depending on if you're talking about a statistic or a parameter. So if you were ever asked to calculate variance or for either a sample or for a population, then you would just use the formulas that we have here, but just not take the square root. So let's go ahead and play with this data set here. You're like, oh, we're going to pick the big data set. Yes, we're going to pick the big data set. So we know what our sample mean is. We'll be using our sample standard deviation formula because we know this is a sample. And for convenience, I think we should go ahead and organize our data with a nice pretty table. And I'm going to work from smallest data value to the largest data value. And I'm going to go through this quickly because I'm going to show you a different way in just a little bit as well for how to work this out. But so what you're going to do is you're going to take your data value, you're going to subtract off the mean, and then you're going to square it. You're going to do that for all of your data values. And I just worked from smallest to largest just to keep myself organized as I was doing it. So you take data value minus mean and then square it. So looking through this first column is just all 28 data values. In the second column, I did data value minus the 100.25. So that's what the second column is for all of them. And then the third column is just squaring what the second column is. So negative 98.25 squared is 9,653.0625. So you go through and you do all of this. And then we're going to add up this third column. We take these sums, that gives us that value there. Our denominator, number of data values minus 1, 28 minus 1. So we're going to do subtraction, then division, then take the square root, and we get 52.113569. And yes, I understand if you have to pause so you can go through and do these calculations and feel comfortable with it. Standard deviation is not necessarily fun to find by hand. I like for you to be able to see the formula, but don't stress if you're not liking calculating it by hand. I will be showing you how to do this nicely on the calculator as well. And as far as rounding, we would go ahead and round this to 1 decimal place as well. So 1 decimal place more than your raw data. So 52.1. All right, before we get into using the calculator to do some things a little bit more quickly, we're going to talk about z-scores really quick. So a z-score is basically a standard measurement showing you how many standard deviations away from the mean a data value is. So you're going to take your value minus the mean and divide by the number of standard deviations. Divide by your standard deviation size. And that tells you how many standard deviations away from the mean that you are. So we have our data set here. We've found our mean. We've found our standard deviation. And I have a couple extra decimal places here. And I should have used x bar, not mu, when I typed this. We have a sample, not the whole population, so we should be using x bar instead of mu. But so what if I said, let's find the z-score for the number 49 and then the z-score for the number 45. Okay, well, the z-score for 49, we're taking 49 minus the mean and then divide by the standard deviation. Again, make sure that you're following order of operations. You're getting negative 0.98. And again, we can do this for the other value that we're asked to find it for. So we're asked to find the z-score of the number 145. So 145 minus 100.25, divide that result by 52.11, keeping at least one extra decimal place here. That gives us 0.86. Both of these values here are z-scores. Z-scores can be negative, they can be positive. Z-scores are going to be negative when your data value is smaller than your mean. Z-scores will be positive when your data value is larger than your mean. A z-score of +1 would mean that it's exactly one standard deviation above the mean. So the z-score of negative 0.98 means it's really close to being one standard deviation below the mean. And a z-score of 0.86 means it's getting close to being one standard deviation above the mean, but not quite one standard deviation above the mean. We're going to talk about z-scores pretty much all semester long, and they'll be really handy in chapters 6 and 7. Now, your calculator can definitely help you calculate means and standard deviations. To do this, you're going to enter your data into a list. Then you're going to be using the one-var stat function to find the mean and the standard deviation. And I should say that this is for if you're using like a TI 83 or 84 series calculator. This is any version of the 83 or 84. So you're going to enter your data into a list and then you use the one-var stat function. And entering data into your list, in order to do that, if you have your 83 or 84 calculator in front of you, you're going to press the stat button and then you're going to choose the edit option. And then it should have a nice list menu. You'll type a number, hit enter, type a number, hit enter, and so on. Once you've typed all of your values, you'll quit out of there. Then you'll go back to stat. You'll go over to calc, and the one var stats option is there.